This is part 2 on how we know about the structure of the hydrogen atom, or evidence about the structure of the hydrogen atom. This is where we left off with this diagram showing the ground state and 4 excited states that are possible for hydrogen. Each of these corresponds to a certain photon of energy that we see given off by hydrogen when it's excited. So let's look at the conclusions again. Apparently hydrogen can emit only certain energies, and those energies are the difference between the ground states and the excited states. Probably should say among those, because everything doesn't go back to the ground state immediately. It may also exchange between excited states. So there are only certain energies possible in hydrogen again, and so we use this term. There are discrete energy levels, meaning separate, definable, recognizable energy levels. And so the term energy level just means a certain amount of energy, and we're going to use the term energy level a lot over the next couple of chapters. All hydrogen atoms are exactly the same. They all have the same energy levels. We always get the same spectrum from hydrogen, no matter what. All right, so let's look at a comparison of what we might expect versus what we see. There's no reason to expect that we should get anything but just a continuous, anything's possible from a hydrogen. We excite a hydrogen, we get anything out of it as it de-excites. We give it a certain amount of energy, we get the same amount of energy out, and any amount of energy ought to work. But it turns out that that's not what happens. Instead, there are these discrete levels of energy that actually cause changes in the atom. There's the ground state. There are excited states above that. So this is what we observe from the evidence, as opposed to what we might assume would happen just based on our knowledge of everyday life. All right, so we say then that the energy levels are quantized because only certain quantities are possible. That was at the time a very radical idea, and it still is, because it's not what we see. We look at a light bulb and we see it continuously give off light. We don't see that it gives off chunks of light or packets or photons of light, and that we can only get certain kinds of light or certain amounts of energy out of an atom. This is a radical idea. However, it's the one that we're going to base our model of the atom on. Another comparison here. If we had a ramp, we could have any possible amount of energy, but the quantized energy level says that we have basically a staircase of energy that we can step our way up to higher and higher energy levels, but only one at a time. If you were walking up the steps, you couldn't have an energy between 2 steps because that just wouldn't work. So Niels Bohr was a Danish chemist, Danish physicist really, and so he looked at this information and he took the Rutherford model that was around at the time, and he modified it to what's known as the Bohr model. You may hear people talk about the Bohr model. It requires the electrons to be in certain orbits, and those orbits are the energy levels that we've been talking about. So an electron can only be in a certain orbit around the nucleus. It can't just be anywhere, and it can exchange from one orbit to another orbit, and when it does that, it exchanges energy. Okay, again, this is a radical idea, dramatically different than what we would probably have assumed for the atom. Okay, and so this is kind of a summary of that new model of the atom. Then instead of the planetary model, we have a nucleus. The electrons are constrained to be in certain orbits. They can, however, change between one orbit and another. That takes energy. And then when they're in that other higher orbit, they will jump back because it's unstable, and we will get the emission of a photon of radiation when that happens. All right, we're going to stop here, and we'll pick the story up and continue with the Bohr model and see where that goes.